So good morning, everyone. I want to begin with a short caveat. I work for Tableau Software, but this isn't a Tableau talk. So you really don't want to draw any conclusions about Tableau's interest in Scala from this, or about, you won't learn anything about Tableau's support for Spark or MongoDB, or relationships and partnerships with other companies that might be represented here. And Tableau tends to integrate with everything, so those relationships do exist. And I don't do this work for Tableau Software. One thing I will say, though, is if any of you have a secret desire to build query processing infrastructure in C++, just quietly grab my attention in the corridors afterwards, and we'll go hide our shame and talk at an undisclosed location, because we are hiring. But at any rate, I really do love Scala, but it's something I do in my spare time. Okay, so I'm going to tell you about a personal journey overall and then focus in on a particular part of that journey. About a year ago, I decided I wanted to learn what it took to integrate Apache Spark with a database system that it wasn't already integrated with. And I kind of poked around a little bit to decide what to integrate with, and I was curious about MongoDB. I noticed that it's becoming increasingly important, particularly in the last year or two. I think of it as almost the epitome of a non-relational database, and collections have no a priori schema, so I saw it as a particularly difficult integration in some ways, or a particularly challenging one. So I make no value judgments about MongoDB. I think it's kind of interesting, and I think it stretches us as a community, and that's really the attraction for me. Now, I used to advise graduate students many years ago in another life, and sometimes people would come to me with things that were kind of an awful project to get started on something with. And in retrospect, I think maybe this was an awful starter project because there was so much to learn, but I had a lot of fun, and maybe you'll find some of it interesting, and maybe you can benefit from some of my experiences. And also, one of the interesting things that happened is that after I got started on this, the external data source API of Spark SQL was introduced, and I got particularly interested in that. Again, if you work at Tableau, you're kind of interested in integration with other data systems or easy ways to integrate, so there was just a curiosity that was already in place there. So this talk focuses on using that API and maybe helping other people to use the API. There are lots of other aspects of what I've had to deal with in the past year that are really interesting, and I'm not going to talk about them. Things about how to take advantage of MongoDB partitioning and then map it to partitioning in Spark, how to infer a schema from a MongoDB collection, managing connections to the database, particularly in a partition setting, type mapping between MongoDB types and Spark types, actually generating the MongoDB query. These are all interesting things, but I really won't talk about them. My agenda, so I'm going to give an overview of the state of the art as I perceived it when I got started on this project. I'll talk briefly about Spark's JSON support, because that was what kind of got me interested and gave me the impression that maybe I could succeed at integration with MongoDB. It seemed kind of analogous. Then to basic RDD level integration, and then move on to Spark SQL and kind of how its API fits together, and then introduce the external data source API and how to use it and how it interacts with performance issues, which were really, I think, the part that I find most fascinating, and then give you an overview of how it all turned out for MongoDB, or has turned out so far, and some of the lessons that I've learned. Okay, so the state of the art as I saw it then was I saw that Spark did support JSON. You could read a JSON file, and Spark would deal with it reasonably, actually infer a schema for it, as I'll describe in a moment. And you could make complex references in queries down into nested documents and elements of arrays and so on, and get complex results back, get arrays back, get documents within documents back in Spark SQL. And it dealt with nulls reasonably. So if you tried to delve down into a document that didn't exist in certain records, in certain JSON documents, it treated it as a null. So a reference through a null was a null. So it was all quite tidy. And I now know that perhaps that's not that surprising because of Spark's desire to be reasonably compatible with Hadoop and with HBase, I guess. I'm not sure if those were the actual motivations, but I was a little surprised and impressed then. So then, Where did I get my ideas about how to actually achieve this? I was by no means a Spark expert, and I'm still not a Spark expert. I looked at the existing MongoDB connector for Hadoop. Some people actually use that through Spark. I don't know if they've actually gotten around to a native connector. I looked at the existing open source Cassandra connector for Spark, which is actually pretty advanced, and it's actually where a lot of people start to learn this kind of stuff. And then I didn't know about Calliope at the time, and actually I just heard about it in a talk yesterday, and I'm actually keen to learn a little bit about it. Okay, so that's where I moved. That's where I started reading code and learning. So I'll just give you a teaser for a moment. What I noticed at that time with Spark's JSON integration is that you could present it a simple document and it would infer a reasonable schema for that document, right? I'm using some features I'll actually introduce later if you're not familiar with them for showing what schema Spark has inferred. And for a single document, it's fine. And if then you might presumably you have more than one document in your JSON collection. If these documents aren't in conflict, then the schema is kind of just the obvious merger of the schemas in the individual documents. The problem with inferring a schema for JSON, of course, is that the schemas of the documents can be in conflict. Foo can be an integer in one document and a nested document in another document. So what do you do? Spark takes a very pragmatic approach to that, is that it really just starts to approximate the schema and starts throwing in strings. So there's some loss of functionality there, but you can actually keep querying, and you can keep delving into deep structure, and you can keep getting complex fragments of JSON documents back. So I viewed it as it works reasonably well. It makes reasonable compromises, and I moved on from there. Okay, so the way one tends to begin to integrate a data source with Spark is to create a custom RDD to implement the abstract class RDD. So most people who are looking to figure out how to do this look at the Cassandra connector. I think it's on GitHub. I might be confused about that. And see how it's done there. And now that's a rather sophisticated implementation. So the abstract class RDD is really the Spark secret source from the point of view of the integrator. And what you have to do there is provide a way to describe the set of partitions and then how to get the data for each partition, right? Assuming that you're going to want the data partitioned, which you eventually will for good performance. And then Spark uses your implementation in the usual RDD lazy way when it needs to get the data for individual partitions. And then you actually also have to implement the trait partition. From Spark's point of view, that's just an ID. It's just, the partitions have IDs 1, 2, 3, etc. And then anything you need to squirrel away in your implementation to know how to get a partition, what the partition represents, maybe it just represents a certain key range, information that you've queried out of MongoDB metadata or whatever database you're using. You can store in your implementation of partitions. And you'll have access to that when you need to. A tip that I would bring up, and at a number of places here I've got tips on how to get started easily. You won't necessarily get good performance just by following these tips, and then also about where I think some of the pitfalls are. So a tip is get started with nothing is forcing you, except for performance considerations, nothing is forcing you to partition your MongoDB collections in this case or anything else. You can do everything in one collection, in one partition. And then once you've got that working, move on from there. And that partitioning can be a very difficult and involved topic if you're motivated to get data out of your backend as quickly as you possibly can. Okay, so what does this look like in code? Just a sketch. So you need a class that extends RDD, and it's parameterized with whatever record type you're going to define for the data you're returning. And I happened to use just just a wrapper for the Java bindings for the MongoDB query results. And then, so partitions is the array of your partition implementations. And then compute is how Spark tells you which partitions it wants you to return an iterator on. And there are lots of complexities you'll find in implementing this properly. You have to do resource management. Probably at construction time for this class, you'll have to go and get some metadata out of the database. You'll have to pass in what table or collection or whatever you need to connect to. And then in the compute method, you'll have to make sure you do some cleanup. And again, it's outside the scope of this talk, but cleanup can be a little bit tricky. You want to make sure you're not leaking connections to your database and so on. And a question up the front.
So it looks like you put information about the partitions within your Spark types. And I'm wondering if I mean, it sounds as though you sought to gain performance by doing so. At any point, did you regret having put awareness of partition, MongoDB partition information, into your classes here in Spark?
I haven't yet, but on the other hand, the partitioning work I've done is not that sophisticated, right? I do observe MongoDB sharding. I don't necessarily observe it well. For example, I map one MongoDB shard to a partition, which probably isn't the right thing to do in general. It's just not something I've delved into anywhere near as deeply as, say, the Cassandra people have, and they've really gone to town with that issue. Looking at what they've done, if you're really serious about that, then I'd look at what they've done. Okay, so moving on to Spark SQL, zooming in. So Spark SQL provides a way to, one way or another, register RDDs as database tables and then query them using SQL, using your existing SQL knowledge, essentially. It's arguably the least mature feature of Spark, but it is very powerful. And the APIs were, I think, marked experimental until Spark 1.3.0 when they were stabilized. There was kind of an upheaval right at that point of stabilization. That was when the data frame class that you've heard about in a couple of talks already, perhaps today and yesterday, was introduced, and I'll say something about that. And you know, to illustrate how powerful this can be, you can even use it to join tables from completely different data sources. Although, as I'll get to, that's perhaps not something that's going to be very efficient in the near future in Spark, although other people may know better than I do when that'll become efficient. So the thing I found about Spark SQL in general is that it deals with surprisingly well with non-relational data, and more smoothly and naturally than, say, Apache Drill. And I don't mean to be unkind to Apache Drill. I think it's very powerful. But I would describe the Apache Drill view of non-relational data as, if your data isn't relational yet, you haven't hit it with your baseball bat enough times, right? You keep massaging the data within your Drill query to make it relational enough for Drill to deal with it. On the other hand, MapR has gotten involved with Drill. Ted Dunning's talk at Data Day Seattle back in June actually suggested to me that maybe Drill is going to be moving in the Spark SQL direction. Just as a point of interest. So just a very simple Spark SQL example here without using an external data source, registering a collection of objects of some case class, and then registering them as a temporary table, and then doing a very simple select star query from that temporary table. Then we get back a data frame on which we can call print schema, and that's where we got this lovely representation of the inferred schema, and then we can print out the data frame in a tidy format that I won't bother to show you here. So just a very trivial example. What are the components of Spark SQL? For our purposes, the really important ones are data frame, which is you can think of it as actually the data that's being queried, but also the results of a query are also a data frame. And they contain a schema, that is, what is the schema of the data in that data frame. And they also contain an RDD of rows. And a row object is really basically, for our purposes, an array. It's a lot like the I've forgotten what the results, individual result objects in JDBC are, but it's the same kind of idea. Its API is kind of similar. So this was the subject of the upheaval in Spark SQL in 1.3.0. It used to be that the relevant class was a schema RDD, and it extended RDD of row. Data frame contains an RDD of row, and both of them contain a schema. And there's a nifty DSL for the data science people who are used to R and that sort of thing. That's not relevant to this discussion. And then, so schemas are basically, the schema type in Spark SQL is called struct type. These types all live in org misspelled Apache Spark SQL types. And you just see a very simple example here of how to put together a type that's just a row of in this case, an integer and a string, and then you can see how to construct the corresponding row object that corresponds to these schemas. So in general, these rows are not self-describing. If you traverse a row, wanted to operate on it in some way, you kind of have to traverse the row in lockstep with the struct type to know what's actually in it, even to know what the names of the fields are in general. So now we come to the kind of the core of the talk, Spark SQL external data sources. So they introduced the ability that in Spark SQL you can use DDL, the data definition language of SQL, to register, to refresh, to list and deregister external objects as if they were tables, among other things, right? And so then these objects can be queried using Spark SQL DML, the general query language. And in recent versions, this data can actually be, the registration can be persisted in the Hive metastore and the objects can be updated. This is a little unclear in the slide. It's the definition of these external objects that can be persisted. So you specify the connector type by naming its class, and then you specify the actual object and the connection properties by passing a property bag in that's eventually passed to a constructor in your implementation. And so a key thing is that the API allows the addition of these data sources without rebuilding Spark. You just drop the implementation in, well, not a class path, this being Spark and being distributed. It's in a few class paths, and that can be a little bit fiddly. And this is in contrast with drill, where unless this has changed very recently, you can dynamically add additional instances of a pre-established external resource type. But if you want to add a resource type, you actually have to add code and rebuild drill, is my understanding. And there may be some trickery that's not well publicized there. So as I said, this was introduced in Spark 1.2.0. It's been evolving since then. And one of the wonderful things that happened in the 1.2.0 release is that the pre-existing data sources that were supported were actually re-implemented in terms of this API, which was a great thing because the API wasn't at all documented at that point, so that was the only way you could find out how to use it. And those data sources actually provided pretty nice examples. This model is, I think, really beautifully designed for ease of adoption, as I'll show. It's perhaps not designed for optimal query execution, and I would imagine that there'll be some development over time so that you have the option as an implementer of an external data source or an integrator of an external data source to opt for easy implementation or really efficient execution, or hopefully first the easy implementation and then to incrementally improve it. And there are elements of that already in the design. The Spark SQL DDL that I was talking about, so really the relevant part here is create temporary table. You give it a name. If you don't give it a schema, the schema is expected to be inferred. And you say what the qualified class name is of your implementation for this connector, and then you pass some options. You can also specify a select to actually populate the thing, and then you can describe and refresh table and so on. For this talk, I'm focusing on registering existing data as a temporary table and inferring the schema, and then being able to query from it. I've experimented with some of the newer features like updating and being able to create the table from a select this way, but I haven't really delved very deeply into that yet. So the API components are in the package, Org Apache Spark SQL sources. An interesting thing that's happened as these have changed and extended is that there's a little bit less inheritance between the various traits and so on. I guess that was a philosophical thing. But there are really three kinds of reusable things here, traits and abstract classes and such. One is basically the providers, which are these are what you have to implement to have something you can register with Spark SQL. Then the relations are just essentially to really the way the API holds on to what you've produced, and then the scans are your description of how you're going to pull data from the external data source, right? Essentially what happens here is that the Spark query compiler, so Spark SQL query compiler makes table scan calls on your API, and you're going to then give it the table data, return the table data that it wants. And there are lots of nuances here that I'll get into now. So what's the recipe for creating an external data source? You have to implement the provider class, and this is called when you register a table. You have to implement one or more versions of create relation, then it returns your table scan class as a base relation. That's how the API deals with it. And then you need to, and it also implements the trait relation provider, a schema relation provider if you're going to have the user specify the schema. So regular relation provider if not, schema relation provider if the user's going to provide the schema and you're not going to infer it. And then creatable relation provider if Spark is going to pass in a data frame for you to send out and persist in the external data source. Then you need to implement a table scan class. This implements the base relation abstract class. And then you need to choose a build scan overload depending on which of the table scan traits you implement. We're going to get to that in a moment. This is called when somebody actually queries. It can optionally implement insertable relation if you actually want to support updating. Okay, and we'll see some outlines and then some examples as well. So relation provider, again, you need to implement a create relation. So just in plain relation provider, it takes a SQL context and that property bag that the user handed over when they registered the table. For a schema relation provider, you'll notice that there's also a schema at the end of the argument list for passing that in. And then for the creatable relation provider, you have to specify what happens in the case of a conflict. And then otherwise, the difference is that in addition to here the SQL context, save mode parameters, you also have a data frame. Here's the data to go and persist. Okay. Base relation and insertable relation. So base relation is really a lot of the substance here. This is where you have to provide to Spark SQL. Spark SQL uses this to find out the schema that you've inferred for this data or the schema that it had previously passed in. And then you optionally can override the size in bytes. This is a hint to the cost-based optimizer to give it some idea of how large the table is for purposes of join optimization and so on. I haven't actually experimented with this yet, but it could be important for performance in certain cases. And then the trait insertable relation is if you actually want to support updating, as I said. So for performance, the two important things to think about are filter and projection pushdown. If you just implement table scan, then that means that the Spark SQL optimizer is just going to ask you, give me this table, the whole table, please. Give me that table, the whole table, please. You'll have to return all of it, even if the query just needs one piece of data. And so then Spark SQL will do all the work. That's great. That's a great way to get started. So that's my tip there, is to actually do this first. But from a performance point of view, obviously, this is going to be hopeless. So what are filter and projection pushdown? Projection pushdown is when you make it possible for the optimizer to say, I'm only interested in these columns. Could you just give me these columns? Although there's a caveat here. And then filter pushdown is, well, the query had some filters, and I'm going to massage the filters so that they're relevant to your table, because the query might have involved several tables. The optimizer figures out which. Here are the filters. Would you apply these, please? queries, use the underlying database to execute those filters efficiently, send back only the relevant columns and only the relevant rows, and then Spark SQL has to do very little work. Now, the intriguing thing about Spark SQL, though, is that it actually reapplies the, well, I should stop doing that. It actually reapplies the filters after you've passed the data back. It doesn't, one way you can view it is it doesn't trust you to apply the filters correctly. I think a more charitable and positive way, and actually a realistic way, is that it doesn't force you to apply the filters. So it'll give you this bag of different kinds of filters resulting from the query. Maybe some of them, well, I'll talk about reasons to ignore them, but you might have multiple reasons for ignoring some or all of those filters. It also may choose not to give you all of the filters. It may keep some for itself to execute just because of the way the query plan that it infers works. But again, the more filters you apply, this will be more efficient. Spark reapplying the filters will actually be pretty cheap if you return a little data. Then let's see. The main thing, and I'll harp on this a little more later, you need to make sure that your query isn't too restrictive. You don't want to fail to return data needed for the correct answer to the query. That's really important. So filter is very easy. Projection is a little bit more finicky. If you implement the version of the table scan where it expects you to project, you actually need to return just the columns that Spark SQL asks for, which may be a surprising set of columns. It may have a surprising order, and I think I've even seen it ask for the columns in a different order from the order in which you specified it in the schema. So there are lots of case classes defining the various kinds of filters, and they've been dribbled out in various releases. I guess I put an asterisk on 150 because unless it's happened in the last couple of days, it's not out yet, but equal null safe seems to be slated for introduction there. And I've highlighted OR in the 1.3.0 introductions because it's a little bit dangerous. So why would you ignore filters? Well, notice that they're being dribbled out a few per release, and this is a healthy project. There'll be lots of innovation over time. So when you build a connector, you might be worried about, well, what if new filters are introduced? Well, you can just, hopefully you can just ignore the new filters that are being introduced until it suits you. So either they didn't exist when you wrote your code, there's no corresponding filter in the system, in the back end you're using, or you think maybe it's inefficient there, it's not worth pushing through, or you ran out of time to implement it, or you're just busy. There's a tip about these filters. These were all straightforward until and, or, and not were introduced. If you get a filter that is with a disjunction of two things, and for some reason you can't translate one part of that disjunction, you better not drop it, right? Because now you're going to start returning too few records rather than too many. So in these and, or, and not combinations, you need to make sure that if there's a subfilter you can't implement, you replace it with true effectively by massaging the whole expression tree or just putting in a filter that corresponds to true in that part. Okay, I predict that's going to generate a few bugs in a few implementations. So then what are the scan traits? So there's table scan, you just return a row, you get told nothing. Pruned scan, you're just told the required columns, note that they're strings. Pruned filtered scan, you get the columns and the filters. Catalyst scan is something I haven't delved into, but it's intended to achieve greater performance, and I think we'll see this develop over time. Simple examples of what kind of behavior you can expect. So a very simple select on the left-hand side. Catalyst will request the column A and will give you the filter A greater than 5 to optionally deal with. So this is my test whether I've put the audience to sleep. In this second example, I'm saying that the requested columns are going to be A and B, but the query is select A. So anybody, why is Catalyst requesting both columns A and B? In this case, it's select A from T where A greater than B. Anybody? That's correct. I think the suggestion was that that the Spark SQL will reapply the filters after the data comes back, and it can't apply the filter A greater than B unless it has access to both A and B. So this is actually an interesting consequence of this real ease of adoption approach, that it's another case where there's a loss of efficiency because extra data has to be, you might have a very good implementation of filtering in your connector, but you still have to pass back the extra data because unless you use unless you use the Catalyst version of the Catalyst trait, you are required, there's no way to stop a Spark SQL from reapplying the filter. A caveat that I think is kind of important for MongoDB, once you get into complex expressions, everything works fine, but Catalyst never asks you for these complex expressions. It actually has no way to ask you, and I'll finish up in just a moment here. It has no way to ask you because it's just passing you a string. So it just doesn't. It doesn't push down filters on them at all, and it just asks you for the top level column for the inferred schema. And I'm going to have to move forward a little bit. Just an example of generating a Mongo query, fairly basic. Is this powerful enough for MongoDB? Yes and no. Yes, it's powerful enough for the expressivity. Maybe not, in that you'll get awful performance because of what I just showed you about complex expressions, if it happens to be important to your query. And also, arguably, it's not practical for aggregation, right? Group by clauses and so on, because there's no way to push those down to the back end. So I'll pass by my hookup slides. And then, so the summary is that this all started out simple but poorly documented. It's become much more complex, somewhat more complex, but better documented. And it provides you the option of a really simple integration to get started. And I think that might be a winning idea, although there might be some things to tweak. And contrast this with Apache Drill, where you really kind of have to bear the full brunt of the complexity of the optimizer, or quite a lot of it, to integrate with it. I applied this to what's probably the most problematic DBMS, short of the graph databases, right? And even then it wasn't too bad. I think I have some serious concerns about performance for deep document references and aggregation. And it could have been easier if the API dealt with complex references. And finally, I'll say I don't really understand the performance characteristics in practice. It's really seems decent for easy examples, and we know that there are cases where it could be deeply problematic. There are lots of other interesting technical issues. I'll pass over those. And for more information, my blog, A River of Bytes, kind of chronicles my learning experiences along the way. This is all available open source. Don't try to put it in production, please. It's really more, you deserve what you get, really. And maybe I do too, but that's another story. And there are some, you can find out about this from a number of other sources. Thanks very much for listening.
So we're running like a little behind, so how about maybe if you guys have questions, go ahead and ask him, but other than that, we'll be reconvening here.